In this video, I will talk about massive MIMO for 5G, in particular below 6 GHz, and I will focus on things like achieving spectral efficiency, link reliability, and low power operation. And I'm Emil Björnsson. I'm an associate professor at Linköping University in Sweden. Wireless communication is something that has been incredibly successful in the previous years. So we see that we have more and more devices and more data traffic for every year that goes. It increases with like 10% in number of devices per year. And that means that in 2016 we had on the average 2 wirelessly connected devices per person in the entire world. And this is growing until year 2022 to 3.6 devices per person on the average. And in addition, the wireless data traffic is growing within 47% every year, which means that in 2016 we were sending on the average in the world 907 megabytes per month per person, and this is growing until year 2022 to 9.1 gigabyte per month per person. So it's an incredibly fast growth here, around 10 times over this time period. And if you count in that we have more devices as well, then it's still 33% more per device. So data traffic is growing a lot, and this is something that has been going on for a long time, and that is why we have different generations of wireless networks, including 5G as being the next generation. And how do we pay for developing new networks and deploying them that can sustain these trends? Well, we need to have a network throughput that is higher in 5G, and the idea is that we should get revenues from new use cases, because of course we would like to use our devices as we did in the past without paying more and just getting higher throughput. But in particular, the new revenues will come from Internet of Things, ultra reliable communication, and a number of different use cases that previous generations of wireless technology has not been able to deliver in a good way. First, let's talk about the cellular network. So in the cellular network, we have base stations that are put on, for example, rooftops or on other types of buildings, and they are serving the users that are in their vicinity, the ones that can reach them with the strongest signal. And this is the type of network that all this 1G, 2G up to 5G is all about. And the network throughput, which is one of the things we can measure in a network like this, is measured in bits per second per square kilometer. And we can divide up into 3 different parts. The cell density, which is the number of cells or base stations that we put out per square kilometer, the available spectrum that we use for the communication, measured in hertz, and the spectral efficiency measured in bits per second per hertz per cell. And if we want to improve the throughput, these are the 3 different categories that we can play around with and try to improve in order to make the throughput higher. So we can have higher cell density, higher spectrum or more spectrum, and higher spectral efficiency. And in future networks, we will need 2 different types of tiers. What we typically have been doing in the years before is that we put the base station closer and closer together. In particular, we need to have short distances in hotspots like train stations, where we have a lot of users in a small area. And that leads to high cell density because we want to have short range. And when we have a short range, well, then we can use spectrum at millimeter wave frequencies that are not propagating through walls very well, because we're anyway just going to aim at the short range. And in those cases, we can make the cell density and the spectrum very large, because there's a lot of spectrum available at millimeter wave frequencies, and therefore we don't need much spectral efficiency in order to get a high throughput. However, even if we deploy a large amount of hotspots, we still need a coverage tier, and that is the focus of my talk today. And we need it to bring coverage to the network from elevated base stations typically, so they can oversee different obstacles that otherwise will be blocking the signals. And they are very important for outdoor to indoor coverage, so they can reach you wherever you are in the building, even if you haven't put up a base station in that particular room. And for that reason, we would like to operate at as low frequencies as possible, below 6 GHz, because then we have a bigger chance of propagating through the walls in a good way. And at those frequencies, we can't find much spectrum, and we can't densify so much because we need the basestation to be elevated, and therefore the spectral efficiency is the factor we need to play around with in order to get a very efficient network. And even if there's a lot of fuss about using millimeter wave frequencies in 5G, because that is one of the key new aspects, it will continue to be the coverage tier that is the main important part in these type of networks. So if you ask Ericsson, for example, they are pointing out that 3.4 to 3.8 gigahertz, that will be the primary band for 5G in Europe, and in other parts of the world there will be similar things as well. And talking about spectral efficiency, which is the important thing in the coverage tier, one of the issues that we have today is that when we put out base stations, the spectral efficiency that we achieve depends a lot on where you are. So if you put out base station at these 4 locations, well, if you're very close to the base station, you will get a very high spectral efficiency. But then the signal power dies out very quickly, and you also get interference from the neighboring cells, which means that for most of the users, you are in a relatively low number here. And if you start to densify network, putting out more base station, well, you get more peaks, but it goes down more quickly, and you still have many locations here where you will get very bad performance. So by just densifying a network, we get mediocre performance at most places. And therefore cell densification is not a good way of achieving higher spectral efficiency, and higher frequency won't help either, because then things will go down even more quickly when signals are not propagating through walls, etc. So what we really want to achieve is to go from a case here where we only have good performance close to the base station to a case where, of course, we will have better performance close to the base stations, but the signal goes down much more slowly, and therefore everyone in the entire network will have a decent spectral efficiency of, say, 4 bits per second per hertz or 3 bits per second per hertz. In order to achieve that, for the users that are far away from the base station at the cell edges here, we would like to achieve a stronger signal but the same interference level as before. And that is something that you can't do by just densifying. We need a new aspect. And the aspect is beamforming. When you have only one antenna at your base station, you send out the signal towards the user here, and the signal will propagate in all directions in the same way, or at least according to a predefined antenna pattern. And that means that users in a neighboring cell that are located over here, they will get a lot of interference. However, when you start to adding antennas, what you can see here is that the signals gets more and more directed towards the user. You can form a signal beam directed towards the user. So this is with 8 antennas. Then you can see that there are still interference that are going out in some other directions. So the blue color here marks a stronger signal than the yellow one. But the main beam is towards the user here of interest. And when we go out to a large or massive number of antennas, we are able to direct the signals through beamforming very narrowly, like a laser beam, towards the user. And then you can barely see much interference that are around this. So M here represents the number of antennas, and that is what we will do in this talk. We will call M the number of antennas. And the more antennas we have, the narrower the beam will be, almost like a laser. And you will achieve something called an array gain, which says that the signal becomes M times stronger when you have M antennas. And in dB, that becomes 10 log 10 of M. And it's less interference leakage in that direction, so we can really achieve a stronger signal at the user without causing much interference to users that are in other cells around here. And the massive MIMO concept is based on this idea. So massive MIMO stands for massive multiple input, multiple output. And the main characteristics here is that we won't like to have base station with a lot of antennas, say 100 or 200 antennas. And we use these antennas to direct signals towards desired users, as I just described, but we also can use it to serve multiple users at the same time, being located at different spatial locations, so that their beams are not overlapping very much. And for example, we can, with 200 antennas, serve up to, say, 40 users without any problem. And the key here with massive MIMO is that there are many more antennas than users K. So high spectral efficiency is achieved here by having many simultaneous users, strong directive signals without having much interference leakage. And massive MIMO came originally from Marcetta, Thomas Marcetta, who worked or submitted a paper called Non-Cooperative Cellular Wireless with Unlimited Number of Base Station Antennas, where he really showed what is happening when you have a huge amount of antennas in the network. And what they really do is combine the best concepts from the Mimo literature in the past decades and do it in a multi-user Mimo setup. And he received a number of prizes for this type of work. And when this was submitted in 2010, I don't think anyone was thinking that today we will see this as a key technology for 5G already. One of the main characteristics of massive MIMO is that it provides favorable propagation. So what does that mean? Well, with a little bit of math, say that we have two users. These users are communicating with the base station, having many antennas, namely M antennas. The channels to these users are represented by two different vectors, H1 and H2, and these are M-dimensional vectors. Favorable propagation then means that if you normalize these vectors, so that you only look at the direction of them, well, then these directions are orthogonal. So you take the inner product of them, they become zero. That means that the base station can fully separate the users both when it sees the signals that are transmitting in the uplink and when it wants to transmit signals back to them in the downlink. And in practice, you won't see exact result where this inner product is zero. However, here's a measurement campaign from 2012 from Bell Labs in Stuttgart. And they put out the base station that they were building, and they measured the signal at a number of different locations here. And here they show what happens with the inner product, absolute value of it, as you increase the number of antennas at the base station. And their measured curve is this one, and the theoretical curve for the channel being independent and identically distributed Gaussian vectors, well, then it will behave like this. And we say the same trend in practice as in theory. The inner product goes down with number of antennas. And as soon as you start to have 40 or 50 antennas, well, then two users' channel will be fairly orthogonal to each other. And that is why having just 8 antennas today will not bring us much orthogonality. So a massive MIMO requires at least to have, say, 50 or 64 antennas. How would you deploy such a large number of antennas? In particular below 6 gigahertz? Well, an antenna have typically a size that is half a wavelength times half a wavelength. So the lower the frequency, the larger the antenna will be. But this is an example of a 3-sector 8 antenna LT advanced base station. That I took this picture in Nanjing in China. And this is a site that has 4 panels here, 4 panels here, 4 panels here. That's what you see here. And each of these panels is one of these antennas, having 2 inputs with different polarization, and therefore it acts as 2 different antennas. However, if you look inside of it, what you will see is that there are, for example, 8 different cross-polarized antennas, and each polarization is fed by one signal. And then these 8 antennas in one polarization is just used to create a fixed beam in a certain direction. So that is how we use this in LT, 1 input per polarization. In massive MIMO, instead, we would like to control each of these elements separately. So we will have 1 input per antenna element. And that means that the number of antennas that you can put on a site that is as large as current sites will be, well, each panel here contains 8 antennas of each polarization. So 8 by 8 becomes 64 per sector. And in total, on a base station like this, you already have around 200 antennas in network. So I would say that the first type of massive MIMO that we will see in practice will be upgrading current base stations, making sure that we have as many inputs as we have antenna elements. And we really don't need any sectorization anymore. We don't need to treat this site as being 3 different base stations. We can treat all the antennas as just 1 base station and beamform all around 360 degrees. And the equipment size is similar to the top of the line LT that we have today, and it will be massive in numbers and not in the size of the base stations. What is important is that the spatial multiplexing that we are going to do here requires what is called digital beamforming. And how do we deploy or implement the beamforming here? Well, we send the same signal for all the antennas, but we vary the phase and amplitude per antenna, and we also vary the phase and amplitude per subcarrier depending on which users are active and how the signal looks like, or the channel looks like at that particular subcarrier. And what the spatial multiplexing means is that we design for each signal a phase and amplitude on each antenna and subcarrier, and then we just superimpose them to form the beams. So if you have a base station over here, we have two different users here. We need to figure out how the signal is going to bounce on different objects. You see here, there is no line of sight components, so it's only multipath components that will reach the different users. And when we have figured that out, we can send out the signal with adjusted phase and amplitudes so that they are arriving coherently here and reinforce each other, all the multipath components. And we can do this with both of the users at the same time. In order to do this in a good way, we need a digital beamforming implementation where each antenna gets its signal directly from the digital baseband. So we can just decide on exactly which signal we want to have, put any phase and amplitude on every antenna for each signal, and change it between subcarriers. The alternative approach that people are talking about, in particular when it comes to millimeter wave, is to use hybrid beamforming, where we cannot adapt the amplitude from the different antennas. We cannot adapt anything between different subcarriers, because from the digital baseband we send out one signal for each of the users, and then we use just phase shifters to combine them for the different antennas here. In that way, there is only one beam for every subcarrier, for every user. There is no power variation between the different antennas. And in that way, it was very difficult to generate good beams this way, in particular in difficult situations like this when you don't have line of sight. And therefore, digital beamforming, giving us the full flexibility, is the future, even if we might see some hybrid approaches, in particular for the vertical beamforming domain in the first implementations of 5G. In order to direct the beams in the right way, we need what is called channel state information. And Thomas Morissette have famously said that channel state information isn't everything, it's the only thing. Because we need to really know where to point the beams. In particular, the more antennas we have, the more narrow the beam is. So it's easier that we miss a user if we don't know where to put it. And the conventional approach to point beams is something called the grid of beams, where we say, for example, if we have 8 antennas, we create 8 different angular beams pointing in different directions. We send one signal through each one of them, and then we'll let the user measure which one is the best one, and then it just reports back the index of that one. And the good thing with that approach is that it's fairly simple. You can just explain it in a simple way. It works irrespective of if you use a time division duplex mode or a frequency division duplex mode. So in the first case, the uplink and downlink is separated in time. In the second case, they are separated in the frequency domain. In any case, just let the user report which beam that is the best one for a particular band. The problem is that there is never a perfect match, because you need to predefine where the beams are going to be, and therefore the user will have to choose between some of these fixed beams, and if they are not perfectly located in the middle of one of them, well, then there will be a lot of inter-user interference between different users. So this mainly works well when you only have one user, so you don't need to care much about interference. Massive MIMO, what we really want to do is base all the beams on uplink channel estimation. So you let the user send a pilot signal, a known signal. You let the base station estimate what it receives, and from that it estimates the channel for the users. And the good thing with that is that you get a well-matched estimates to the channel. You don't need to make any assumptions about how the channel looks like from the beginning or require them to be in line of sight or anything. You just measure what you see. And that becomes scalable also with the number of antennas, because you just estimate the channel in each of the antennas separately. So it doesn't get worse when you have many antennas. The only bad thing here is that it only works in time division duplex mode, where you change between uplink and downlink on the same frequency. And for that reason, you can measure the channel in the uplink and use it also for downlink transmission. And therefore, massive MIMO for 5G is particularly useful and will deliver all the things I'm talking about today in TDD mode. And one of the very nice things with massive MIMO is that it can achieve very high spectral efficiency. And in particular, the two groups at Bristol and Lund University, where they have big massive MIMO testbeds, they have set several world records in spectral efficiency. So in, for example, 2016, they made this video where you're showing the world record that they made. They had 128 base station antennas controlled by this hardware here. They served 22 single antenna users with 256 QAM signals. They operate over a 20 megahertz band at 3.5 gigahertz, and then they were able to deliver a 145.6 bit per second per hertz per cell. That's their spectral efficiency. And this is a screenshot from the video that you can find on YouTube. And of course, are these big numbers practical? Can we achieve this in practice? Well, in the cellular network, you will, in addition to what they measured here, also have interference from other cells. And you won't have as control environments. You can't use this large modulations. But you can still do multiplexing of tens of users. That is practical. That's been demonstrated as well by these testbeds. And you're probably going to use lower order modulations in practical systems. So here is an example of that, where we have made simulations with hexagonal cells. We have a base station in the center with M antennas. We have K users around it, and then we have a large number of hexagonal cells. And these pilot signals that are used to do the channel estimation, they are reused in the cells having the same color. And here we have a pilot reuse factor of 3, and that is important in order to get good channel estimates without much interference from the neighboring cells. But when you do data transmission, all the cells are active at the same time. And the total spectral efficiency that we measured in this simulation depends on the number of antennas. It goes up like this with the number of antennas, and this is the number of users that we serve in order to get this maximum number. And what you can see is that with 128 antennas, well, we get maybe half or slightly less than that as compared to what they showed in the Bristol world record. But you can still reach up towards the number of 140 bit per second per hertz if you have many antennas and you serve many users at the same time. So high spectral efficiency is what you really can achieve per cell. This is much higher than an LTE system where you might more have 2, 3, 4 bits per second per hertz per cell. And here we deliver something on the order of that to every user, but we serve tens of users at the same time. So that's the key thing here. High spectral efficiency in total per cell by serving many users, not necessarily by giving high spectral efficiency per user. On the other hand, they can be active at the same time, all of them. So this was what I wanted to talk about when it comes to high spectral efficiency. But 5G is more than just mobile broadband. In particular, 5G is supposed to deal a lot with the Internet of Things and get new revenues by serving the wirelessly connected society, where machines, vehicles, everything will going to be connected, and there are supposed to be a huge number of small sensors and there are other things that will be communicating in the 5G networks. And the use cases for this are very different from mobile broadband. For example, one case is that we would like to have a very high link reliability. This is important when you have factory robots that are connected, or if you use 5G for traffic safety applications. And particularly this use case is called ultra-reliable low latency communications. So reliability is the important thing, but not to have a high spectral efficiency. You can trade that away in order to get more reliable communication. Another case is something called massive machine type communications, where you have many low-cost sensors or actuators deployed everywhere. And they are thinking that maybe we will have 50 billion such devices by year 2020. And these will do sporadic transmissions, send a small amount of data, and you want the battery to last for 5 years. So can Massive Mimo play a role here? Well, if you deploy Massive Mimo 5G network in order to deliver great mobile broadband, hopefully we can use these antennas to also deliver these type of services that are important in particular to get new revenues to these networks. And yes, I will describe how Massive Mimo helps towards these two goals. And one important thing is what is called channel hardening. So when you send the signals between the base station and the user, with Massive Mimo you get narrower beams. So if from the beginning most of the signal are sent out in this angle from the base station, well then with more antennas it will be sent out in a much smaller angles. And that means that the number of multipath components that will be really involved here will be smaller, and therefore the channel variations will also be smaller. There are fewer multipath components that can make the link bad sometimes. And this is called channel hardening. And one way of looking at it is to say we have a channel between this user and the base station. It's m-dimensional when you have m antennas, and it's complex Gaussian distributed, zero mean, and an identity matrix as covariance matrix here. Then the variations in the effective channel reduce it with m. So what do I mean with that? Well, if I look at this channel, take the squared norm of it and divide with the number of elements, well, this is what you would get if you do beamforming for this channel. Then the mean value of it is 1, while the variance goes down as 1 over m. So what this really means is that if you look at many different channel realizations, well, then they will be random variables, but their distribution will be more and more concentrated around their mean value. So if you have a very small number of antennas, the variation can be large, as illustrated by this red curve here, where I've just generated one realization of h here and added more and more antennas to it. Then in the beginning there are large variations, but then they start to concentrate around the mean value, which is the black curve here, as you add more antennas. And you can statistically compute percentiles and see that with 10% probability you are below here, with 10% you are above here, so with 80% you are in between these two different lines, and those lines becomes more and more concentrated around the mean value. And here we see some double benefits about massive MIMO. Well, first of all, if the mean value of this one is 1, well then the squared norm will grow with m, so that is the array gain again. But the variations around the mean value also reduces, relatively speaking. And how is this important? Well, if you talk about link reliability now, then with massive MIMO you can achieve higher reliability. So if you only have one antenna and you look at different channel realizations randomly generated, well then your channel gain measured in this squared norm will be varying a lot. And you will lose the data packet if the square norm is below some kind of threshold that you put into your system. So if you put the threshold somewhere over here, well then all of the channel realizations that are below it will cause your packet to be lost. However, with massive MIMO, you will get something like this instead when you have 100 antennas. So the variations are much smaller, and it's fairly easy to put a threshold here where you always are above the threshold, and at the same time this threshold is at a high value. So it's less likely to lost packages and easier to put a large threshold in massive MIMO. And if you lose the packages less often, well then you also need fewer retransmissions, which results in lower latency. So this is one of the important things that massive MIMO can have towards link reliability. Another interesting thing is that resource allocation is made simple in massive MIMO. So in conventional network, what you need to do is you look at your time and frequency grid here. Each color represents one user in the network, and you put out the user at some different locations in the time frequency grid and let them transmit at that time and be silent when the other users are active. So in massive MIMO, since the variations are very small, there is no point of saying that, okay, one user should be at one place and another user should be at another place depending on when the channels are good or bad. And there's no point to separate them because you only are allowed to have one user at a time. Well, with massive MIMO you can have 40 users at a time. So therefore you can give the entire time frequency grid to all of the users. Of course they won't need them all the time, but there's no need to schedule users based on their channel fading. You just give the users as much spectrum as they need whenever they need it. So that makes scheduling and resource allocation very simple in this type of systems. When it comes to this array gain that makes the signal m times stronger when you have m antennas, there are two ways to exploit this array gain, and these are important for Internet of Things application as well. One thing is that if you only have one antenna, you might cover the area inside this white cell here, and outside that one the signal will be too weak in order to communicate with the users. Now, if you have m antennas, you have a range extension. So you can have 10 log 10 m higher path loss from the base station and still be able to serve the users. And for those users that are close to the base station, well, they will get higher rates for those already covered, and you will reach new places. For example, reach indoor to places where it's very hard to reach otherwise. The other option is to go for low power operation. So you can cover the same region as before and let users transmit with less power. So depending on where they are, you can show mathematically that you either get 10 log 10 m dB less power, or maybe only half of it. That depends on that the channel estimation quality also reduced when you cut down on the power. But somewhere in between this is the amount of less power that you can use in networks. And this is important if you have battery powered users that are just transmitting packets now and then you can increase the lifetime of their batteries. And for example, if say that you have 100 antennas, then this will tell you that you can reduce the power with a factor 10. And instead of communicating in the downlink with 40 watt, you can transmit from the base station with only 4 watt per base station by using this type of things. And since you have 100 antennas, well, now you will have 40 milliwatt per antenna. So it's really little power per antenna. And that will really simplify the hardware design. It will essentially be like making each antenna at the base station like a cell phone antenna, instead of having some high power antennas as in current networks. So low power operation can both be useful for the user devices to reduce their power and to reduce the power from the base stations. And you have to choose which kind of mix of this you want to have and what mix of range extension and low power operation that you would like to have in your system as well. Massive MIMO can be very important to support the Internet of Things by using these properties. So a typical scenario in the Internet of Things is that you have a lot of sensors everywhere and you would like them to transmit some data now and then. And you're supposed to support path loss up to 150 dB, which could be a range up to tens of kilometers or reaching down to a basement somewhere. And this communication is typically done in the uplink towards the base station. And you usually use quite a narrow bandwidth so you can get the highest SNR. So maybe use a 20 dBm transmit power that represents 100 milliwatt when you're transmitting. You add the antenna gains, you subtract the path loss in your link budget here, and you also subtract the noise power. And then at this limit you might get an SNR of minus 5.7 dB in this case here. That could be sufficient for some binary modulation with some repetition coding, so you're protecting your data transmission as well. And if you just only send a few data packets per day, then you can do this with very low energy per package. With Massive MIMO, with 100 antennas, you can improve on this, because if you go for link or range extension, you will have an SNR that grows with up to 20 dB if you have 100 antennas. And that improves also the link reliability because of channel hardening, so you have to retransmit fewer packages. Alternatively, if you go for the low power operations, well, then you can reduce the transmit power with up to 10 dB here, which represents going down to 10 milliwatt instead of 100 milliwatt. And if it's a transmit power that's a dominating cost here, well, then you can increase your battery life with up to 10 times by using 10 times less power. So as a summary, Massive MIMO for 5G below 6 GHz can help out with all of the three main use cases in 5G. Mobile broadband applications, where you can deliver very high spectral efficiency with Massive MIMO by multiplexing many users. And you will get great improvements, in particular at the cell edges, and that's one of the important things as compared to cases where you only densify the networks in the past. In addition, you can deliver or help out to deliver ultra-reliable low latency communications, where the channel hardening alleviates a lot of the small-scale fading hassles that you have in those type of systems. That leads to fewer retransmissions, more predictable performance in the networks. And finally, Massive MIMO is also very important for massive machine type communications, where you can either extend coverage and have a more cost-efficient deployment because you have to put up fewer base stations in order to reach all of these sensors. Alternatively, you can reduce the transmit power for battery power devices, and maybe you can use a mix of these two in the networks. So these are the main good things with Massive MIMO for operation in 5G below 6 GHz. If you want to learn more about Massive MIMO, you should check out our blog at massivemimo.net. where we are every week writing blog posts about Massive MIMO with 5G focus. Check out our YouTube channel, where you can, for example, see other videos. I had a talk called Massive MIMO for 5G, how big can it get? Which is focusing on how many antennas you can put out and what benefit that gives. And you can check out my new book called Massive MIMO Network, Spectral Energy and Hardware Efficiency, which is a 517-page book where you can find MATLAB code available on our webpage, massivemimobook.com. And from time to time, we also have special offers for buying the book for a good price. So check out our webpage for that. Thank you.